Unit 5, Thermochem, pages 53 to 58, Heat of Formation. Definition of formation reactions. A formation reaction is defined as elements in standard states yield 1 mole of the products. And this is important that you have only 1 mole of products. The words in standard states means the natural form of the substance at 298 Kelvin and 1 atmosphere. Remember the natural forms of the common element. So here you have your diatomics, hydrogen gas, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's their natural form. And then everything else tends to be in its normal state, like carbon and aluminum. S8 is for sulfur, and that would be considered the natural form of sulfur. Here are some examples of formation reactions. So C6H6 is the product. And so if I'm looking at the product, I'm going to look at the elements that make up that product, in this case carbon and hydrogen. On the left side, I'm going to write them in their standard state or natural form. So carbon naturally exists as just C, plus hydrogen naturally exists as a diatomic. Once I've written the elements in their natural forms, then I can balance the equation. 6 carbons, 3 times 2 is 6 hydrogen, 6 hydrogen. This works because my product has only 1 mole's worth in front of it. Here, N2O4, my 2 elements are nitrogen and oxygen. They both exist as diatomics, so I have N2 plus O2. Then I balance the equation. We have 2 N's, 4 oxygens, so 2 times 2 makes 4 oxygen. Finally, NaCl. The standard states are going to be sodium solid, and then chlorine is a diatomic. So I'll have Na solid and Cl2 is the diatomic. When you balance this equation, you would normally get 2 Na plus Cl2 yields 2 NaCl. However, because you have to have your product only 1 mole's worth, then we're going to multiply the entire equation by 1/2. That's going to get rid of this 2 and make it 1. And so instead of having a 2-1-2 ratio, multiplying all the coefficients by 1/2 gives me a 1-1/2-1 ratio instead. And so now this is considered the formation reaction of NaCl. So example 5.18, write the formation reaction of H2O liquid. Well, I'm going to write H2O as my product, and then it's made up of hydrogen and oxygen. Both of those exist as diatomics, so I'm going to write oxygen O2 and hydrogen H2. Now I want to balance the equation. 2 hydrogens, 2 hydrogens, 2 oxygen means I need a 2 there. And so this now gives me 4 hydrogens, so I'm going to place a 2 here in front of hydrogen. Because that has to be 1 mole, I'm going to actually multiply all of this by 1/2. And so 1/2 times 2 gives me 1 hydrogen, plus 1/2 times 1 gives me 1/2 oxygen, yields 1/2 times 2 gives me just 1 water. And so I'm going to end up with H2 plus 1/2 O2 yields H2O liquid, and that would be the formation reaction for water. Here are some examples of incorrect formation reactions for water as a liquid. So this one is incorrect because H2 exists as a gas in its natural form, not as a liquid. This one is incorrect because it's not 2H, it's H2 because it's a diatomic. So just H by itself is not the natural form of hydrogen gas. This one is incorrect because you don't have just 1 mole of product, you have 2. And it has to be changed, the coefficients across the equation, to have only 1 mole of product. And then this is not a correct way to write it because reactants are not elements. You can't have, you're supposed to have each element, not a compound, as your reactants of a formation reaction. Calculations with formation reactions. Formation reactions are useful because the heats of reaction for formation reactions can be found in common tables. Heats of reaction for a formation reaction are written as delta HF with a little degree symbol at the top. Pay attention to the superscripts and the subscripts. The F stands for a formation reaction, and the little 0 stands for at standard state, which is going to be 298 Kelvin and 1 atmosphere. The enthalpy of reaction for any reaction can be found using heats of formation given in tables. In this equation, M and N represent the stoichiometry of the reactants and products. So you can find the delta H of a reaction when you take the sum of the coefficient times each product's formation, delta H, minus the sum of the reactants' coefficients times their delta H of formations. The reason why this equation works is discussed below. Example 5.19. Calculate the delta H of reaction for this reaction using heats of formation in thermodynamic tables. So here's my reaction, and then here are the heats of formation. So I'm going to start with the products. So it's going to be delta H of reaction is equal to, we're going to take the sum of the products. I'm going to take the coefficient of 6 times the delta H of formation of CO2, which is provided here, negative 393.5. Notice it's in kilojoules per mole. Just going to write the kilojoules. And we're going to add that to 3 waters in the liquid state. So I have 3 times the delta H of formation of water, which is negative 285.8 kilojoules. And then I'm going to subtract the sum of the reactants. So it's products minus reactants. I have C6H6 liquid, and there's only one, so it's going to be 1 times positive 49 kilojoules. And then notice that O2 gas does not have a delta H of formation, and that's because in its standard state it's going to be 0. So you can assume if it's not given to you in the table that it must have a delta H of formation of 0. And so now I'll close the parenthesis. When we do this math, we get a delta H reaction equal to negative 3,267.4 kilojoules. The principle behind heats of formation calculations. This section illustrates why this equation works. The delta H of reaction is equal to the sum of the coefficients times the delta H of formations minus the sum of the coefficients times the delta formations of the products minus reactants. Think of this reaction right here as taking place in 2 steps. Step 1, you'd have C6H6 plus 15/2 oxygen yields us these elements in their standard states. Step 2 would be these elements in their standard states, and then the formation of the final products, which is 6CO2 plus 3H2O liquid. So if we look at the chart here, we look at the enthalpy, or energy it takes in order to break these bonds and form into their elements, and then we look at the enthalpy it takes in order for them to reform into these products. And the difference between these two is the delta H of the reaction. So you can take your products minus your reactants. So here's the note card for this section. Formation reactions are going to occur under standard conditions of 298 Kelvin and 1 atmosphere. Elements in standard states yield 1 mole of products. Must modify coefficients in order to have only 1 mole of the product on the right side of the equation. Diatomic elements have paired standard states, i.e. hydrogen has to be H2, not just H. And then an example of a formation reaction here is C2H5OH, where I have the elements carbon, hydrogen, and oxygen. So here's carbon, normally exists as a solid, plus H2 diatomic, and it's a gas, plus O2 gas, yields the C2H5OH liquid. And then you have to balance the equation. However, because there's a 2 here, we have to divide all the coefficients by 2, so we have 1 mole of product, which is going to yield us this as our formation reaction, a 2, 3, 1/2, 1 molar ratio. And this is going to be represented by the delta HF, that's the enthalpy of formation at standard conditions, heat of formation under standard conditions. And you can get the delta H of a reaction if you are given a table of delta H formation values by taking the sum of the products minus the sum of the reactants, keeping in mind that you have to multiply the coefficient times the delta H of formation for each reactant and each product.